Hi everyone, welcome to Inspiration Exchange number 43 today. So today we'll be talking about informed meta-learning and active task disambiguation. Before we jump into the session, we just wanted to highlight that the Schaar Lab is recruiting for PhD positions. So if anybody is still interested, please apply on the lab website. We look forward to getting your applications. And then today's session, we'll be kicking it off with a talk by two PhD students from our lab on informed meta-learning and active task disambiguation. These are two works accepted to ICLR 2025, and you'll hear more from Kasia and Nicholas in a little bit. And then after that, we'll move on to our roundtable and Q&A with our leading panelists. I'll introduce them more formally once we get to that point, and you'll learn more about who they are then. So without further ado, let me hand over to Mihaela for a few words, and then we'll kick things off with.
Thank you very much, Nabil, and I apologize to you, everyone, for being a little bit sick and not having a voice, but I still wanted to say how excited I am about this session, because we hear a lot about large language models and what they can achieve, but we don't hear at times enough about what they empower us to do that was never possible before. So the area of meta-learning has evolved over many years, and yet, until the paper that you are going to hear about today from Kasia, it was very difficult for us to take human knowledge, powerful synthesized knowledge that we have, and translate that to machines, to models in an effective way. So I'm very excited about the world of informed meta-learning and the possibilities that it can open. And I'm very excited about the panelists and what they have to say about how this new way of thinking about meta-learning can hopefully transform that. And then in the second work, I'm also excited because often when we try to communicate complex problems and tasks to machines, but also when we, with each other, for instance, in the process of diagnosing a patient, we are trying to really communicate what is exactly the set of issues that play a role to identify and disambiguate the type of diagnosis we want or the type of task we want to achieve. There are issues associated with ambiguity, problems that are not correctly specified, either because we don't know how or because we are not precise enough, or issues like in diagnosis where we need to unravel the problem we want to solve, the illness that we have, through a set of questions. And I think what Nicholas and Kasia have done provide a way of thinking to both these two areas. Finally, I want to thank very much to James, Sebastian, and Andres for being with us and helping us think about the opportunities that these two papers provide. Thanks a lot.
All right. Hi, everyone. My name is Kasia Kowalczyk, and I'm a second-year PhD student in the lab. And today I would like to present to you my work on informed meta-learning, in which we will look at the problem of integrating domain knowledge from human experts into machine learning algorithms. Let us begin with a little bit of a background motivating this work. One of the big challenges in deploying machine learning models in the real world is the scarcity of data. When the data is scarce, we must rely on the in-domain knowledge of experts that guide model design in order to encode the expert knowledge as the so-called inductive bias of a model. Inductive biases can be seen as the prior probabilities of different solutions within the hypothesis space of a model. The stronger the inductive bias, the fewer samples of data we need for the model to converge to an optimal solution. A well-designed model is such that its hypothesis space is large enough to contain the ground truth solution. It also must exhibit strong preferences for solutions that closely align with the ground truth. So for instance, if we take the problem of image classification, a convolutional neural network is a well-chosen model as its inductive biases help the model to learn, for instance, spatial invariances. On the other hand, if we take a linear regression model, it would be a very poor choice for this task, as likely the true solution would live outside the hypothesis space of the model. And in contrast, a generic neural network, while it does contain the true solution, its inductive biases are very weak, and therefore it would require a lot more samples of data to recover the optimal solution. So how do we go about selecting the right inductive bias? Well, essentially, every conventional machine learning problem can be represented with the following 3 elements. We have a context data set, also known as the training data set. Here we will stick to the convention of using the word context data because it's more common for the meta-learning setup. We also have target data, which is also known as the test data. And this is some held out data that we want to make predictions on. And in addition, we have some knowledge about the learning task. In many cases, this additional knowledge won't be represented explicitly, but here we will assume that we have access to its explicit representation. For instance, it can be just written down as a sentence in natural language. And in case of a, say, one-dimensional regression, this knowledge could convey information about the monotonicity of the expected fitted function. Our goal is then to construct a learning algorithm that predicts the target values based on the contextual data. And the inductive biases of this learning algorithm should be such that they reflect the knowledge encoded in the knowledge representations. So how do we actually integrate the inductive biases encoded in these representations into the machine learning model? Conventionally, this problem is solved in a, I would say, very much manual way, because we start with the machine learning practitioner interpreting the available in-domain expert knowledge and then designing a model that encodes this knowledge as an inductive bias. This can be achieved, for instance, with some specialized loss functions by applying various data augmentation techniques or designing a custom model. The final fitted model is then obtained by training on the provided context data. Typically, this process is, however, quite labor-intensive, and its success relies on the extent of which the domain expert knowledge can be encoded into the machine learning model. An alternative approach to this problem of inductive bias selection is to automate it with meta-learning. Meta-learning enables us to automate the process of inductive bias selection by pre-training our model on a collection of related learning tasks. By training the model on this collection of related training tasks, the model learns an appropriate inductive bias itself, such that after observing the training data for our task of interest, it can be quickly adopted to it, given just a few samples of the data. However, the paradigm of meta-learning does not enable the human domain expert to take control over the inductive biases that are learned during the meta-training. This meta-learning process is quite black box in nature, and it depends in an intractable way on the collection of available meta-training tasks. So given this, we want to find a new method of inductive bias selection that is A, automated, meaning that it requires minimal human engineering efforts, and B, it enables human interpretable control such that the selected inductive biases are directly based on the in-domain expert knowledge represented in its native formats. Here, the focus is on knowledge representations presented in natural language. To address this problem, we proposed a new model of automated and controllable inductive bias specification by a knowledge conditioned meta-learning, or in short, we call it informed meta-learning. While conventional meta-learning learns effectively a fixed prior over the hypothesis space of a model, we instead consider learning a knowledge conditioned prior that maps arbitrary representations of expert knowledge to knowledge conditioned priors. The learned mapping from the knowledge space to the hypothesis space of a model can be seen as a translator between the human interpretable knowledge representations and the hypothesis space of our model. So after successful meta-training, such a learned mapping could in theory enable us to generalize to previously underrepresentations of knowledge and then assign higher probabilities to solutions that are in agreement with the information conveyed within those knowledge representations. In order to enable learning this form of a mapping, we must assume access to a collection of training tasks represented by context data, target data, and then their corresponding knowledge representations. We assume that context and target data sets are generated according to an underlying unobservable function f, which is sampled from an unknown stochastic process. And given this function, the actually observable data is generated by introducing some unpredictable random noise. The knowledge pertaining to each task is then is represented in a human interpretable format, such as natural language, and contains truthful but likely incomplete information about the underlying function of interest. So in a nutshell, the training of an informed meta-learner starts from gathering the collection of meta-training tasks. We then optimize our model to find meta-parameters that maximize the likelihood of the target data given the contextual data points and the additional side information. This object is optimized against the entire meta-training dataset. After meta-training is completed, at test time, we can make informed predictions by providing the learner with a sample contextual data and, if available, the additional expert knowledge. So in this example on the right-hand side, we can see how just given 3 data points, the uninformed predictions are associated with a high uncertainty in the observed region of the input space. But given the information that the fitted function should be increasing, the prediction interval narrows down to just the set of increasing functions only, which is precisely what we would like to see. In our paper, we also present a theorem which enables us to theoretically motivate our proposed approach. The key insight from that theorem is that successful integration of knowledge into machine learning model via informed meta-learning necessarily manifests itself with improved predictions. To test this claim, we start with some simple synthetic data experiments. We construct regression learning tasks by sampling ground truth functions from a family of sinusoidal functions and let the parameters and let the knowledge encode the values of the parameters A, B, or C, which here guide the slope, the oscillation frequency, and the bias terms of the functions. And then we wish to investigate if by informed meta-learning we can learn the mapping between the values of these parameters A, B, C and the space of a plain neural network. Here we look at the sum predictions made with our already trained informed meta-learner. With no context data or external knowledge provided, sample predictions represented by curves in gray in the top left corner exhibit a high variation. They represent the heterogeneous prior distribution learned during the meta-training. After conditioning our model on the additional knowledge about the value of the parameters, which are the sample predictions here on the right, we can see that these predictions adapt accordingly. For instance, if we specify the value of the frequency parameter, all sample predictions represent sinusoidal functions with the given frequency of oscillations, which is exactly what we would like to see. As we provide the additional contextual data, here represented with just one data point in black, predictions adapt to it. And now we have more data points, so we adapt to it more easily. So we can also confirm that the knowledge improves prediction by just looking at the loss of our predictions. And indeed, this is the case with the informed predictions here represented with green result in a much lower loss than the uninformed ones. This validates that our informed meta-learner has successfully learned to integrate knowledge into its predictions. In the paper, we also discussed the differences on uncertainty reduction given sample data and given the expert knowledge. So sample data essentially conveys information about the local value of a function in a given point. So this is a local reduction in the uncertainty, whereas for knowledge representations, we could convey information about much like more global properties of the function, such as the frequency of oscillations or slope in this simple example. However, this toy example with synthetic data serves us only to anchor the key ideas of informed meta-learning and just like a sanity check that the proposed approach actually works. In a real-world application, we would be interested in cases where knowledge is presented in its native format, which in most cases will be just our natural language. But with the current progress in large language models, there is nothing stopping us from testing this idea. So in our paper, we look at two examples where the knowledge is provided in natural language. The first one is a time series prediction problem where the additional knowledge is represented as an oracle weather forecast for the given day, and the data that you want to predict is the evolution of the temperature throughout the day. In the first column of this figure, predictions in gray represent the uninformed predictions of a model, and the predictions in green are predictions sampled by after our learner has been meta-trained and informed by the weather prediction forecast presented here on the right. The black dotted curves stand for the ground truth temperature. We can see that also in this case, the model learns to correctly interpret the information conveyed in this weather forecast, narrowing down its prediction intervals. And in the second example, we consider informed image classification, where the task is to predict the class label of a bird, given a small few-shot sample of training images, and additional knowledge about the characteristic features of a given bird class. As expected, the predictions made with the informed model, having access to this additional information about the features characteristic for a given bird class, are significantly improved upon pure data-driven predictions. And also the knowledge informed prior that we have learned during meta-training enables us to make zero-shot predictions based just on the textual descriptions provided, which is not possible without this informed pre-training. So in summary, in this work, we introduce a new perspective on inductive bias specification via informed meta-learning. This enables us a way of automating the process of inductive bias specification in a way that is fully controllable by in-domain human interpretable knowledge. Learning this map between knowledge representations and the hypothesis space of a model establishes in a way a communication bridge between the human experts and machine learning models. And as a result, this enables us a direct integration of the domain expert knowledge represented in a human interpretable way into final predictions, leading to significantly improved data efficiency. If you would like to learn more about this work, please do check out the full paper, which is now available on arXiv and which will be presented during the upcoming ICLR conference this April. We will now move to the second part of this inspiration exchange, which is centered around another paper involving large language models and uncertainty. So let me now hand over to Nicholas, who will give us an introduction to this new problem and its challenges.
Hello, my name is Nicolas Astorga, finishing my second year of studies. Today we're going to present active task disambiguation with large language model that was also accepted on ICLR 2025 with Kasia Miasio and first authors and Tennyson and Michaela van der Schaar, co-author of this work. So let's start motivating this work by commenting about the problem setup. So let's imagine that we are in a scenario of human-AI interaction, where the human or user has a problem in mind, a problem statement, and the user wants this task to be solved by an agent or LLM. The problem statement is ambiguous by itself, so if the agent tries to generate solution, it could find many of them. But only one of the solutions is truly aligned with the user intentions. So we need to discard many of the solutions to really align with the user. We do this by generating a clarifying question. So there could be many clarifying questions, but only one of them could be the most informative one. So the objective of this paper is try to the most informative clarifying question.
In order to solve this problem, we must first determine what it means for a question to be informative, and what do we mean by an ambiguous problem statement in more formal terms. We let S denote the problem statement posed by a user, where S belongs to the space of natural language, which we here denote by sigma. So we have the problem statement, we have the sample solution, which is denoted by lowercase h, and we also have a set of ground truth acceptable solution, which we denote with curly h star. So this is the set of solution that the user would be inclined to accept. But we don't a priori know what is this set. We further decompose the problem statement as consisting of two parts. We have requirements R, that a hypothetical solution that is that would be accepted by the user should satisfy, and we also have some additional context that can guide the LLM's generative distribution, and also can inform us about the internal preferences of the user. We have these two distributions. The P phi is the generative distribution of the LLM, and P star is the likelihood of a solution being preferred by a given user. We can think of P star as being essentially that we can decompose it into two parts. So we have the objective indicator, we have the subjective part, which is user specific. And yeah, okay, now we move to the definition of the task ambiguity.
Okay, so to define the task ambiguity, we already have our formal terms. And in the end, we say a problem is ambiguous if the proper solution, the solution set of solutions that fulfill the requirement is a superset of the solution set that are aligned with the true intention of the user. Which is basically, if we see a density distribution, we can say that there is some green part, which is the true intention of the user, and which is only a subset of the all compatible solution. And of course, there could be a gray area, which is the preference distribution of the user with respect to this space, but we really don't have access to this distribution, and we only have access to what the agent is generated, which is in green. So the ultimate goal in the end is generate a solution that as we have more information, the solution that if we sample from the agent distribution, all the samples should belong to the true intention of the user, which is the H star. However, there are two challenges. The ambiguity inflates uncertainty, which means that with highly ambiguous problem, the risk of generating an unsatisfactory answer or solution is high, and there also is heterogeneity of individual preferences, which means that the preference of individual user may vary vastly, which means that the most likely solution according to the vote of the average population is not necessarily the one that the individual wants or is looking for. So we propose a strategy that we start with some problem statement at some time, at some iteration T0, for example, and we want to extend this amount of information as the time progresses by asking clarifying questions. So maybe we start with a problem statement at time T, which is a tuple between the requirements and the context. But after we ask a question and the user give the response, we can extend the problem statement into a problem statement T+1, which has more information now. And to make this more intuitive, so if we have a solution space at some time T, what we basically we are doing is like we start with some distribution of the agent, and this is distribution is narrowing because we have more and more information. And also the compatible solutions are also is also narrowing because we have more and more requirements.
Yeah, great. But although this strategy seems sensible, obtaining the answers to the clarifying questions from the user or another form of an oracle may be quite costly. And the goal of this paper is to explore strategies for asking clarifying questions that lead to the smallest interaction costs between the LLM and our oracle. So this figure shows us an overview of a pipeline for iterative task elicitation. First, a user poses a problem S that the LLM may attempt to solve by generating a candidate solution H. Given S, the LLM may also ask a clarifying question denoted by Q. And if the LLM could generate a sample of hypothetical questions, we then would like to find the question Q star that maximizes some form of a utility metric that defines the usefulness of a question. After selecting this best question, we then present it to the user who provides the oracle answer and the problem statement is updated. The remaining question, however, is how to measure the utility of the candidate question.
Okay, so to respond to this question, we took a Bayesian experimental design approach. So in Bayesian experimental design, you usually want to develop the best experiment to reduce the uncertainty about your solution. And in this case, we want to select the best question that we could possibly answer. So we took then an information gain approach to measure the utility. And here we can see the information gain of a question and a given answer, which is basically the difference between the entropy in the solution space minus the entropy after we have this additional knowledge. Of course, in practice, and you can see this like as an uncertainty reduction of how much information is given this pair of question and answer. This could be very tied to information gain. But however, we don't have the answer. We only have the question, and we need to measure the utility of the question. So we instead we measure the expected information gain, which is basically an expectation of the information gain, as the name says, over all the possible answers that we can have given a question and a problem statement. This estimation of the answer has to be done by the agent itself, for example, the LLM, or for external tool, for example, a compiler when we are working with code.
Essentially estimating the expected information gain in the space of natural language is not very trivial. And we also do not know the ground truth distribution P star, which is the distribution of the solutions as likely provided by the user, but we only have access to the LLM generated distribution, which may be misaligned. To overcome this, we will assume that the entropies involved in the expected information gain, we will compute them with respect to the uniform distribution over the space of compatible solutions. Then under the assumption of uniformity, it can be shown that the most informative question is the one that splits our space of compatible solutions into equally sized subsets. In the case of binary question, that is questions of type yes or no, this is the same as just selecting the question that for which half of the hypothetical solutions would result in an answer yes, and the other half would lead to an answer no. A further insight of the corollary that we present in this paper is that if a given question a larger number of hypothetical answers, it has the potential to be more informative, but on the other hand, proposing such a question may be at a higher cost from the user side or another form of an oracle. So our pipeline for active task disambiguation relies on estimating the expected information gain of a set of LLM generating questions at each interaction step. The expected information gain is estimated by first sampling a set of candidate solutions that we hope that it will approximate well the entire space of the solution space. And then we also sample a set of candidate questions. In the next step, the candidate questions are answered with respect to these candidate solutions either by the LLM itself or by using some form of an external tool. And now, based on these pseudo answers, we can estimate the cardinalities of the partitionings that each candidate question generates, and then we select the question that generates the most even partitioning.
Okay, so we now go back and go to the experiment. And the first thing that we try is the game of 20 questions, which is basically a game that is the user is thinking about an object, in our case, an animal, for example, a dog, and the LLM asks a yes or no question to determine what is the user is thinking about. So the goal of the agent is ask as less questions as possible. So these are basically our results, and basically we have the axis here is the iteration, which is basically if you have more, further we progress, we have more information, we have more requirements, so we should be closer to guess the animal that we are thinking about. The y-axis in this case is a rank, is a way of approximating how good is a problem statement, and basically is we do it by using an external agent, an LLM agent. And we basically, given a problem statement, we basically rank all the possible solutions, and then using the ground truth, we can say, oh, we score this amount and this amount, so we can have an estimate of how good this solution is respect to the rank. So our solution is the expected information gain, assuming that all the solutions are equally valuable, and in general, outperform the baselines, particularly when we use less capable model. In this case GPT 3.5, but we also show other cases in the paper, open source models. The expected information gain using logproof is basically using the entropy of the token, and implicit is a zero-shot question generation, and TOT is basically we generate question and the LLM itself retrieves the question that it's making. We guess that in this case that GPT-4o mini is not that our method is not that good, because the LLM itself is generating the question, the hypothesis or solution, and answering the questions. But if we use external tools like a compiler, maybe the LLM is not as good as approximating the answer, which is what Katja is going to present.
Exactly. So in the previous example, we had the case where all the questions, the answers, and the solutions, they all belong to the states of natural language. But we also can test our strategy on more structured problem of code generation, where the solutions are Python programs and the question answer pair form executable test cases. We consider two types of question and answers. The first one is a binary type of question where the LLM generates complete unit tests that the user must either accept or reject, which is essentially like a yes or no type of a question. And then we have an open questions, which are the sample inputs to the function of interest for which the oracle must provide the expected output. The input-output pairs are then transformed into a unit test. And we compare our EIG-based strategy for question generation against simple zero-shot baseline for generating these questions or these unit tests. We assess our strategy and the baseline on the two very common benchmarks, the human eval benchmark, which contains simple queries, and APPS benchmark containing competition level coding challenges. We observed that across all language models tested, the expected information gain strategy for question generation brings significant improvements. In this figure, this figure shows the accuracies where the bars in the darker shade correspond to the strategies for question generation based on expected information gain. And we also observe an interesting relationship that the improvements due to EIG estimation are the highest for models which are considered in general less capable. For the more capable, bigger models, these improvements are more modest. We hypothesize that this ability of generating good clarifying questions requires a form of metacognitive reasoning, that is, it requires the LLM to reason about its own generated distribution and then find some features about the candidate solutions that differentiate them apart. And this is a complex reasoning, form of reasoning that may be beyond beyond the capabilities of some of the smaller models. In summary, in this paper, we identified the need for new reasoning methods enabling LLM agents to handle ambiguously specified tasks efficiently and effectively. We introduced a formal definition of task ambiguity in natural language problem specifications and frame the problem of effective task disambiguation through the lens of Bayesian experimental design. Our results demonstrate that the abilities of many modern LLMs in generating clarifying questions can be improved. And the method that we propose bypasses the need for metacognitive forms of reasoning by shifting the focus from reasoning about the best question to ask to explicitly reasoning about the self-generated candidate solution. As a result, we improve the question generation by relying on the existing capabilities of LLMs in generating diverse and correct solutions. If you would like to find out more about this work, please do check our paper, which is now available on arXiv and will be also presented at ICLR later this year.
Awesome. Thanks so much, Kasia and Nicholas. And then now I think we're ready time on to the panel discussion. And now to introduce our panelists, firstly, I want to thank them all for taking the time to be with us today and for joining the panel. The first is Dr. Sebastian Farquhar, who is a senior research scientist at Google DeepMind. Then Professor Andres Floto, who is a professor of respiratory biology and the co-director of the Cambridge Center for AI in Medicine. And then Dr. Jane Wang, who is a senior research scientist, staff research scientist at Google DeepMind. So I thought I might kick off the panel a little bit with more general questions, and then I know definitely Kasia and Nicholas have very specific questions for the panelists. I think I'll start first with you, Andres, on Kasia's paper on informed meta-learning, especially from like the clinical side, where the paper talks about injecting human expertise into machine learning models. And what type of human expertise do you see from like the clinical perspective that the such methods have like unlocked and you think could be injected into machine learning models?
Thanks for the question, Nabil, and thank you to both presenters. I thought it was terrific, presentations. So that's a really interesting question. I mean, we struggle with the problem of domain experts actually not being experts, having an incomplete understanding of the current state of literature, to have intrinsic biases themselves, as in human biases. And so I love the idea of, well, two things: providing a framework to inject this prior knowledge or domain knowledge into the problem. But it does open the question to answer the one that you asked, is that why not the whole of medicine, or the whole of biology? You know, so why is it limited to? Do you know what I mean? You could have a situation where, for example, in a biological system where you are looking at understanding causal relationships, inject all of biology into that model, and the search space would be narrowed. And you know, you can imagine a really exciting way in which you could speed up the advance of knowledge. I don't know.
And I guess definitely like the natural language integration probably.
Yeah, exactly. I mean, you know, once you get, and particularly when you have LLMs trained specifically on scientific research, you know, on medical research, you know, I think it's really, really exciting. And actually then the domain experts are kind of irrelevant, right? Certainly in terms of formulating the problem.
And then Jane and Sebastian, I guess from your side, from like the more machine learning side, and maybe I'll split it across the two papers, or like ask Jane around the informed meta-learning and Sebastian around the active task disambiguation, of both like your opinions on the papers, but also where do you see there being like research challenges that still need to be addressed, and where the machine learning community can kind of like take it forth from here, like what sort of things should be addressed. And I guess maybe Jane, I can start with you.
Yeah, sure. And yeah, and I also wanted to say great talks to everybody. And I actually really enjoyed looking these over before as well. I didn't realize that they actually are quite related to the things that I've been thinking about and working on. this idea of, yeah, how do you like formulate human interpretable knowledge and constraints, and also like specific kinds of constraints that you might be interested in like at this very moment, incorporate it into a meta learning model or some kind of a model that you want to quickly adapt to new situations. And one of the ways I see this as being quite important is, something I've been thinking about lately is how do you specify a task in natural language in general? It can be quite, ambiguous. I guess this is kind of relating to the next paper as well. But if it's almost easier for you to say, I want to specify a constraint. I want to specify something that maybe can't happen, or that's something that, it is easier for you to specify than to say, this is my goal that I want my agent to do, or that I want my model to follow. And so I think in that respect, it's quite interesting. I was also struggling at first with kind of the difference between context, like your context data set versus the knowledge that you're sort of conditioning on. And I think maybe why this was, like, I think I understand now. It's, first of all, it comes from more of like a human specified perspective. But the kind of meta learning that I traditionally worked with was using memory-based meta learning, where you kind of condition on past history, or you have some kind of a hidden state that you condition on. And it's more of a sequential kind of a model of recurrent neural networks. And so in that way, you can almost think of this knowledge as being an explicit version of the hidden state that you're sort of conditioning on. So it's providing like additional context, but it's in a way where you can sort of inject it from the outside, then trying to get your model to sort of learn for itself that this is what it should keep around in order to condition it. So in that way, I think it's a lot more powerful and exciting.
Sebastian, I guess, can I bring you in?
Yeah, well, so I'll share a couple thoughts on the second paper first, and then I'll also have some thoughts on the first paper as well. I mean, when I read this a few days ago, my initial reaction was, wow, that's neat. And so that's a great reaction from my perspective for a paper I thought was a clever idea. I'm really interested in and curious about this observation that the 4.0 mini model, the gap narrows between this sort of implicit method where you're inviting the language model to think carefully about which question is going to be best for clarification, versus the more explicit model-based version, and this kind of this gap shrinking. And I do think this is a trend. Basically, every time you try to do these sorts of explicit methods, it helps, especially for, weaker models, and then gets less and less important. And I would love to see, I don't know, I often find that if you spend a few days really juicing your few-shot prompting and really optimizing exactly what examples you're giving, you coach the language model to think about the information gain, you coach the language model to think about like which questions are going to bifurcate the space and give examples of how this works. It wouldn't surprise me if you're able to then beat the performance of the more explicit model for these more advanced models, which is not a criticism of your approach. I think it's clever to think about this stuff in this way, but is just a trend that we're going to need to engage with as a machine learning community, that it's deeply satisfying to come up with these algorithms, and personally frustrating when then the large language model just you can just ask nicely, and it sort of does as good a better job, but that's just the world we live in. And so I think exploring that more would be really interesting. The other thing that intrigued me about this is, to some extent, you're relying on an implicit model of like what the user's intentions might have been. And it's interesting to think about what the unknown unknowns there are. So how do you design clarifying questions and dialogue with clarification that accounts for the fact that the LLM model of the user's intentions might be misspecified or partial or only somewhat understood. And that poses some big extra challenges. But all in all, I love this. I feel like we, as a like LLM service providing industry, are just doing a really bad job at clarification at the moment. I mean, this is all providers. I think we're really just leaving value on the table here because, you know, when I think about like a great PhD student is one who asks clarifying questions, is always seeking to understand a little bit better, like what is actually meant here? What is the scope? What's the requirement? What's the request, and so on. And our language models don't do this at all, or in very limited ways. So I think this is a great direction, and really, really cool work.
Awesome. And I know Cassia and Nicholas definitely had questions. So
I maybe can jump immediately to Sebastian. I think you are right. Like the gap is going to shrink every time. I think, but for one case, maybe it will maintain, or you will never like to completely be like if we are very explicit about the solution, and in comparison to think about the question itself, I think there are some scenarios that this gap could be maintained, and I think it's when you really rely on something that the LLM doesn't know. For example, a completely new tool, and using this black box, you obtain a solution. Then it's very hard for the LLM to simulate all this black box and to really reduce the uncertainty just thinking about the question itself. I think in those cases, maybe there is a potential scenario where the gap will always a little bit maintained.
But what if you train the LLM to use tools?
Yes, in that case, you are right. in that case, if the LLM learns how to use the tool and get experience about the tool, then I think I agree with you.
I mean, I think you're spot on. There are types of epistemic processing that are not best done by transformers, which might require real-world experimentation or search or just a calculator. And you know, this is, I think, going to be an area for growth and improvement. Is how it already is. You know, there's a big field of how we do this kind of tool use, and integrating it into this sort of thing is another thing that would be valuable.
Yeah, I will do one last question very short and let to Kasia. What do you think? So I have seen mixed result between using token probabilities. Like, for example, sometimes it helps, sometimes it's worse. In our case, it didn't work. It's too biased. How do you think that the uncertainty will be measured in large language model in the future, or what are the most promising approaches?
I don't really know about this. I don't know if you saw one of the papers I did with some students in Oxford last year. We sort of tried to compute these entropies of these output distributions, and I think we basically ended up finding that the use of token probabilities didn't change anything. Like slightly unclear. We found this annoying, but didn't have a great explanation for why, except perhaps that it was adding too much estimation variance. So my like very vague hunch would be that if you tended the number of samples of your estimator of the entropy to infinity, that the version with the log probs probably would tend to outperform, but that for small sample sizes, the chance that you just get like a low probability thing, which then looks really big when you take the log, is too high. I don't really know. I've slightly moved away from this set of questions, but it was something that bugged me at the time, and I'm still a little unhappy about.
Thank you, Sebastian.
Yeah, thank you both. I have a question regarding the future of informed machine learning in general. So I guess there are two approaches at least to creating models that are guided by some additional knowledge about the learning task. It can be either that we design an explicit algorithm that encodes some form of an inductive bias. Say we implement a graph neural network that has a special architecture, or we could do something very simple, like just use a foundational model and provide all the knowledge that we have in context and ask it to make predictions. And I think that now the community is sort of shifting towards foundational models and trying to make these like pipelines that elicit priors over the predictions from, say, natural language provided as a context in the prompt. So I was wondering, from your perspective, how do you see the future of such informed machine learning approaches? The question is open to either Sebastian or Jane.
I guess I can speak a bit about this. From like, I used to work primarily in meta learning, and in the realm of meta learning, especially meta reinforcement learning, it was sort of, you had to do most of your thinking about the task distribution, because your model was usually general purpose enough that you can sort of get whatever structure you want, like whatever inductive bias that existed in your task distribution. So a lot had to be thought of about, like, what is that task distribution? Am I putting in some kind of weird artifact that I don't actually want? I need to sort of randomize across those things in order to like not get the inductive biases I don't want. But now with LLMs and foundation models, we can kind of count on the fact that they have a pretty general set of useful inductive biases. And that's why a lot of these in context learning kind of prompts just work zero shot. And I think a lot of times we've seen that zero shot tends to be better than even few shot, because you're not kind of washing out some of those useful biases. And then as we're getting longer and longer context, and we're training on more and more data, I think that we're seeing, and we're hitting like the limits of like getting the most optimal scaling in terms of compute and training tokens. We're seeing that, yeah, essentially maybe you can just sort of assume that a lot of the inductive biases will be there, and you just have to coax them out somehow. But I will kind of caveat this with saying that I think that, in my opinion, the foundation models that we have today don't, they are missing some useful inductive biases that humans have. So they're not very good at action understanding. They're getting better at video understanding, but if, I mean, the project that I've been most recently involved with, SIMA, is explicitly trying to get these models to try and act in an embodied environment. And there's where you start to see a lot of the limitations of the kinds of inductive biases of training that you get from training on just internet data, right? So, so I think that there's going to be a lot of work in trying to figure out, well, how do we fine tune, or how do we pre-train to get these additional kinds of embodied inductive biases into these models?
Yeah, and I guess sort of building on that, I think inductive biases are, I think this is like a framing that's very attractive from the perspective of Bayesian inference and a lot of the sort of statistical machine learning literature that, you know, I would say I sort of grew up with, but don't work so much with anymore. I'm almost slightly pessimistic about it as a framing at the moment. And I think it can be very expensive to insert inductive biases into models, unless you know in advance you have quite a specific use case in mind. And I don't mean it like financially expensive. I just mean you often end up sacrificing more than you think you're sacrificing, by making the architectural constraints that add whatever inductive bias you're trying to add. And at the moment, I almost feel like one of the strengths of the large language model paradigm is the generality and the flexibility. And I'm almost more optimistic about combining the generality of the large language models with things like tool use, where you use the right tool for the job, and perhaps the selection of the tool encodes the task-specific knowledge, rather than trying to build that into the large language model, which isn't what you were doing. I know you were using these neural processes, but you know, it's I think there are some interesting questions about like how the way we used to think about inductive bias in the context of things like CNNs transfers to the sort of transformer-based and LLM-based paradigm.
Can I just your comment just kind of made me inspired me to think about something where you can almost think of these foundation models as maybe being like a universal Turing machine or something, where you can kind of assume that they provide general enough capability that you can coax whatever you want out of them. But if you do have a specific use case, it's something where it might just be easier to have a calculator rather than program your universal Turing machine to do the calculation for you, right? It's almost like overpowered in that sense. And so if we're thinking about inductive biases and their usefulness, you almost cannot get away from thinking about also the tasks you want to apply them to, and the kind of the final use case.
Yeah, absolutely. I agree with all that has been said, and I do think that the concept of inductive bias, as we typically refer to it may be getting in a way outdated. So that's why in this work, I sort of try to make it slightly more flexible and not necessarily bound to like the architecture itself, but just as some form of warm starting of the procedure of predicting then later the final values. And definitely exploring further strategies for not necessarily not creating models that are trained from scratch, but rather starting with a foundational model and finding a fine-tuning procedure for helping it to like make the informed predictions. So you could think about a meta-learn like fine-tuning of the foundation model for it to like improve the integration of any contextual knowledge that could be provided in the prompt to the downstream predictions. And this also, on the other hand, raises the question whether we actually need to provide this information in context ourselves, or is there a way in which this contextual information could be elicited by the language model itself based on its vast prior knowledge that it already has based on the pre-training of basically on all of our data that we have in the internet. So yeah, definitely great questions, and would love to explore more of that in the future.
Thanks for that, Cassian. I guess we've probably, unfortunately, started running out of time. I know we do have one question in the chat, and we'll take that, I guess, offline from one of the audience members. And Cassia, you can take a look at that. And then I really just wanted to say thank you so much to Sebastian, Andreas, and Jane for joining us. Thank you so much for taking the time and for contributing.
Thank you very much.
I really appreciate it.
Thanks very much.
And we look forward to seeing everybody next month. We'll be announcing the topic fairly soon.